Okay, today we're going to look at section 4.6, modeling with exponential and logarithmic functions. So we have our exponential and growth and decay models, which we discussed before. We'll let y be a variable changing exponentially with respect to t, and let y sub 0 represent the initial value of y when t equals 0. Then for a constant k, where k is greater than 0, y equals y sub 0 times e to the kt is a model for exponential growth this way. This should look relatively familiar. If k is less than 0, then y equals y sub 0 e to the kt is a model for exponential decay. In other words, dropping down. So writing an exponential expression using base e, if we let t and b be real numbers where b is greater than 0, but b is not equal to 1, then b to the t is equivalent to e to the natural log of b to the t. In a logistic growth model is a function written in the form y equals c over 1 plus a to the negative bt, where a, b, and c are positive constants. So let's look at some of the models we can do with this. The first model we'll look at is the growth of an investment. So we're told that the amount in account for is equal to P times E to the RT. Now let's see, suppose that $10,000 is invested. So that means our P, our principal, is $10,000. And at the end of a 5-year period, so T is 5, the value of the account is $13,771.28. Okay, so that's A. Use the model A equals P times E to the RT to determine the average rate of return R under continuous compounding. So we're talking continuous compounding here. So here's what I know. I know that 13,771.28 is equal to 10,000 times E to the 5 times R. Okay. So first thing I can do is divide by 10,000, which gives me 1.37728 is equal to E to the 5R. Now, if I take the natural logarithm of both sides, the natural log of 1.37728 equals the natural log of E to the 5R. Well, this is simply 5R. And we'll leave this for now. 1.37728 divided by 5, and I get the natural log 1.37728 all divided by 5 equals R. So I can do the math on this with my calculator. Hit the natural log button, 1.37728. Don't forget to close the parentheses and divide it by 5. And I get R equals 0.0640, or roughly 6.4%. And that was what we're looking for. Okay, so now let's look at another one here. How about population growth? Very similar formula. Let's see. No, actually, it is a similar formula. It says on January 1st, 2000, population of Texas was approximately 21 million. So we're going to call that our initial time. 21 million. On January 1st, 2010, the population was, so the population after 10 years, 25,000 or 25,200,000. Write a function of the form P sub t equals P sub 0 e to the kt to represent the population P sub t of Texas t years after January 1, 2000 and round k to 5 decimal places. So k is going to be our growth rate. So how can I do this? Well, first step, what do we know? And we're going to rewrite this as 21 and 25.2 to make our numbers easier. So we know that 25.2 equals 21 e times 10 e to the 10k. Okay. So now we can do some division here. We get 25.2 divided by 21 equals e to the 10k. Take the logarithm of both sides. 21.2 over 21. And we know this is simply 10k. So we know that k is equal to the natural log of 25.2 divided by 21, all divided by 10. So, getting our calculators. Here we go, natural log of 25.2 divided by 21, close parentheses, divided by 10. That gives us k is equal to 0.01823. So that means that P of t is equal to 21 million times e to the 0.01823 times t power. That's our equation. Now, the next question is use the function in part A to predict the population in 2020, round to 1 decimal places. So we want to know 2020, that means t is 20 years. I have 21 times e to the 0.01823 times 20. 0.01823 times 20. This gives me 21 times e to the 0.3646. So 21 times e to the 0.3646 equals. And to 1 decimal place, we get 30.2 million. There's A and B. Part C says use this function in part A to determine the year during which the population of Texas will reach 40 million if this trend continues. So now we want P of t to be 40. And we're going to solve for t. So 21e to the 0.01823 t. Divide both sides by 21. 40 over 21 equals e to 0.01823 t. Take the natural log of both sides. And we get 0.01823 t. Then divide. So we have the natural log of 40 divided by 21 all over 0.01823 equals t. So using our calculator, natural log 40 divided by 21, close parentheses, divided by 0.01823. And we get t of 35.35 rounded to 2 decimal places. So sometime, now this is how many years, so sometime in the year 2035 would be our answer. Okay, the next thing we're going to do is an exponential function with base e. So if I'm given p sub t is equal to 10,000 times 2 to the negative 0.4 t. Write the rule for this function using base e. So the first thing to note is 2 to the negative 0.4 t is equal to 2 to the t to the negative 0.4. We can apply that property we had, which was this here. So this gives me, this is equal to e to the natural log of 2 times t all to the negative 0.4. Okay. Which is equal to e, so log of 2 times negative 4/10 times t. So therefore, $10,000 times 2 to the negative 0.4 t is equal to 10,000 times e, so log of 2 times -4/10 times t, what we have here. So we take the log of 2. That's the log of 2 times our -0.4. And we get 10,000 E equals -0.2773 T. So 10,000, so this equals 10,000 E to the negative 0.2773 times T. Okay, that's our formula. So what's the function for T equals 10? Now if T equals 10, of 10,000 E, this becomes negative 2.273. So what is E to the negative 2.273? Here, second E, negative 2.273. Okay, times that times 1,000 or 10,000. 0.277. Now the book goes to 27726. So if T is 10, that's wrong. This should be 27726T. So when I multiply it by 10, I get negative 2.7726. So I have E to the negative 2.7726 equals times 10,000, and I get 625. I don't think there's anything that complex. Next, we'll look at exponential decay. So we'll use the function q of t equals q sub 0 e to the negative 0.000121 t to determine the age of a piece of wood that has 42% of its carbon-14 remaining to the nearest 10 years. Okay. So how does this work? Okay, so that formula was done from the example 5. So working with that. Okay, so let's see what we got going on here. So if we have 42% remaining at 0.42, that is Q of T, the remaining carbon-14 after a certain time. So we have 0.42 equals Q sub 0 e to the negative 0.000121 t. So then I can take the natural log of both sides. Natural log of 0.42 equals now Q sub 0 at time 0, it was all there. So Q sub 0 is essentially 1. What we're trying to find out is how long does it take for all but 42% of it to be gone. So this is simply 0 point or negative 0.000121t. So I divide 0.00121, and that's going to give me t. This is going to give me t. I guess I should have rewrote that. So let's do it. So I'm going to end up with the natural log of 0.42 divided by negative 0.000121 equals t. Okay? So natural log 0.42 divided by negative 0.000121 equals. And we get t to equal 7,169.426. So 7,170 years. Okay. The last thing we're going to look at is logarithmic growth to model population. So again, the score on a test of dexterity is population. Says population. Let's see what happens there. The score on a test of dexterity is given by P sub t equals 100 over 1 plus 19 times e negative 0.354 times x. Determine the initial score, where x is the number of times taken. So the initial score would be the first time it's taken. Or actually it would be 0. X would be 0. So if we let x why do they do this POT when it's x? Because that's a t or a misprint. So when t is 0, this is 0, that becomes 0, this becomes 1. I have 1 plus 19. So for p sub 0, I simply have 100 over 20, which is 5. Now, use the formula to determine the minimum number of times required for the score to exceed 90. So essentially, I want this to be greater than 90. E negative 0.354. I guess it is x. X being the number of times the test is taken. So when is this going to be more than 90? So I have 90 times 1 plus 19 times e to the negative 0.354 times x. And when is this going to be less than 100? Well, what is this? This is 90 plus 90 times 19. 1,710 times e to the negative 0.354x, and that has to be less than 100. Subtract the 90 from both sides. Oops. E to the negative 0.354x. I can divide, so I have e to the negative 0.354x less than 90 over 1710. Let's see how that division comes out. And messy. So taking the natural log of this, I end up with negative 0.354x less than, and this is what? The natural log (9 over 171), which is what? 3 over 57, which is 1 over 19. That worked out well, didn't it? The natural log of 1 divided by 19. So negative 0.354x. When is that going to be less than the natural log of 1 over 19? And we're actually going to divide here to get x over negative 0.354. So the natural log of 1 divided by 19 divided by negative 0.354 gives us x is 8.317, which is not right. So this is how this works. We made an error in there somewhere. Not sure where, but there isn't a test question on this anyways. So let's end this recording, and I shall see you next time.